Hello, welcome to the second chapter. I'm going to go ahead and start some new toys on this one that I haven't tried before. So this should be fun. Let's see. Let me share my screen. And let me bring my annotate up. There we go. Let's see how that goes, huh? All right. Okay, so this is the outline for the first half. We're going to talk about atoms, um, the fact that elements are made out of atoms, and then what isotopes are. We're going to converse about what a covalent bond is, what a polar covalent bond, and a non-polar covalent bond is. And then finally, we're going to address what an ionic bond is. So basic chemistry in this chapter, and then we're going to finish with acids and bases. So let's get started. The fundamental unit of matter is the atom. In the last chapter, we learned that the fundamental unit of life was a cell. Here we learned that the atom is the smallest unit of matter. As a matter of fact, the word itself is atom. Meaning not or without, and tom means cut. So atom literally means that object that can no longer be cut or divided. The three most important constituents of the atom are protons, neutrons, and electrons. Protons and neutrons exist in the nucleus. Electrons travel around the nucleus, and they are responsible for chemistry. So here's an example. Here's hydrogen. Incidentally, I uploaded a periodic table to this module, so feel free to have that up or print that out. Okay, but here's hydrogen. Notice that it has one proton and one electron. Okay, so how do we know that this is hydrogen? Because of the number of protons that it has. So the number of protons tells you the identity of the element. That is the only thing that matters. It's so special that it has a name. It's called the atomic number. So the atomic number for hydrogen is 1 because it only has one proton. In a neutral atom, because it has one proton, it also must have one electron. Okay, here's helium. Here's the second element in the periodic table. Okay, notice that it has not one but two protons. Okay, this particular helium has two neutrons in there. Okay, but these neutrons do not give you the identity of the element. What gives you the identity of the element? The number of protons, So what's the atomic number for helium? It's 2 because it has two protons. The number of neutrons tells you the isotope. Those are other helium atoms that have different masses, but they are in fact helium because they have two protons. Now, if helium is uncharged, it has two protons and it has two electrons. Because protons are positively charged and electrons are negatively charged, so two pluses and two minuses add up to 0, so there's no charge in a neutral helium. Okay, so to recap, protons are positively charged, electrons are negatively charged, and neutrons have no charge whatsoever. Okay, so what I just finished saying, each element is defined by the number of protons in its nucleus, and this is called the atomic number. Okay, now the atomic mass of the element might vary. So for example, if I had one neutron in here in this helium atom, it would still be helium, but it would weigh a different amount. So it would have a different atomic mass. but the atomic number and the identity of the element would still be helium. Okay, let's see. So the number of neutrons in an atom can vary independently of the number of protons. Okay, a single element can exist in various forms called isotopes depending on the number of neutrons that it has. The example that we like to use is hydrogen. Okay, so here's hydrogen, and there's three known versions of hydrogen. How do we know they're hydrogen? Saying it yet again, it's got one proton, one proton, one proton. If it has one proton, it's hydrogen. However, notice that this one doesn't have any neutrons in it. Therefore, its atomic mass is that of the one proton. Okay. In deuterium, which is hydrogen also, there's a single neutron. The identity of the element is still hydrogen. Okay, here we're going to call it deuterium, but it's hydrogen. And the atomic mass has increased, but the identity of the element has not. So therefore, deuterium is an isotope of hydrogen because the chemical traits have not changed, but the mass has. Here's another version of hydrogen. So this is a third type of hydrogen. This one is called tritium. It has one proton, so the atomic number is 1, but it has 2 neutrons, making it even heavier than deuterium. Okay. I can see the question already. Can you have deuterium oxide instead of water? Can you have tritium instead of hydrogen in water? Yeah, you can have T2O, because after all, this is hydrogen. So you have T2O. It's called heavy water, and it's used in reactors because it's heavy, and it's a tendency to has a higher temperature at which it evaporates. So we actually make this stuff we don't make it on purpose. We isolate it on purpose, okay? But the point to drive home is that all these three are hydrogen because they all have one proton, but the atomic mass varies because the number of neutrons in it. And when only atomic mass varies because of different neutrons, they are called isotopes. Isotopes. Okay, now we're moving to chemistry. Okay, so atoms can link to one another in a process of chemical bonding called covalent bonding. In covalent bonding, atoms share one or more electrons. In contrast, in ionic bonding, atoms do not share electrons. They lose and accept electrons from each other, so the electron transfers completely. Okay, both of these events, both covalent and ionic, are attractions between atoms that carry different electrical charge. In other words, one is positively charged, the other one is negatively charged. Okay. Now, why are we trying to do this? Electrons are always trying to go to their lowest level. Okay. You and I are trying to go to our lowest energy level too. I mean, we only stand up when we can't sit down, and we only sit down when we can't lie down. So everything in nature is trying to go to its lowest energy level. This is also true of electrons, okay? And when they do, they want to, in order to reach that lower energy level, they have to fill out their outer electron shell, okay? What does this mean? Well, here's your periodic table, okay? So feel free to bring this guy out. And what you'll see is that we have these periods going here, okay? For those of you who have had chemistry before, you might remember that this is the s orbitals, these are the p orbitals, these are the d orbitals, and these are the f orbitals over here in the bottom, okay? Now, as far as you and I are concerned, because we're in biology, we only care about up to maybe the fifth row. Why? Because our bodies use iodine, but we seldom go below. I can't even think of a reason for going below that. Okay, so the heaviest element that I know that we use is iodine. So the chemistry that we are interested in, that we are involved in, is everything up here. Okay, so what do we have? Here's our hydrogen. Notice that we have an atomic number of 1. Do you see that? That means that all hydrogen has 1 proton. But look at the atomic mass, is 1.00794. Why are those not the same? Because we have multiple isotopes of hydrogen. The majority is hydrogen, but there's some deuterium that has 2 neutrons, and there's even less tritium with 3 neutrons. But when you average the natural occurrence of those 3, you come up with an average of 1.00794 of those 3 isotopes, okay? Now, we go over here, and these guys are special. These are the special guys, okay? These guys in purple, these are the Kardashians of the periodic table. Everybody else wants to be like them. Don't yell at me. I'm just trying to make it relative, okay? So these are the noble guys. These are the super cool guys. Everybody else wants to be like them. Why? Because they have a closed energy shell, and therefore all of their electrons are at the lowest energy level, okay? So this makes helium a very strange little guy because it only takes 2 electrons to close the lowest energy level. Do you see that? How do we know that it's 2 electrons? Because its atomic number is 2, therefore it has 2 protons. In order to maintain a neutral atom, it must therefore have 2 electrons. So once we have 2 electrons, the energy shell on this guy is closed, and it's happy, and it's not going to react with anything. So the valence electrons, the electrons in the outermost shell, are the electrons that dictate the chemical properties of the elements. And you need to keep this in mind, okay? So in other words, hydrogen is reactive. Why is hydrogen reactive? Because it only has 1 electron in the valence shell. And how many does it want? Well, he wants to be like this cool dude, helium. So he wants 2. And he'll do whatever it takes to get that second one. Are you guys with me? Okay. So we go from there, and now we go from helium to lithium. Anybody care to guess how many electrons lithium has? I'll give you a hint. Take a look at the atomic number. The atomic number is 3, therefore there's 3 electrons. But keep in mind, only the electrons in the valence shell are reactive because everybody else is happy. So what does that mean? That means that lithium has 3 electrons, but 2 of them are happy because they feel like they're helium. So if you have 3 electrons and 2 of them are happy, how many unhappy electrons do you have? The answer is 1, right? 3 minus 2 is 1. So what does lithium want to do? Well, lithium can do one of 2 things. It can either lose an electron and be like helium, or, and this is hard, add 1, 2, 3, 4, 5, 6, 7 additional electrons to be like neon. Which one of those 2 do you think is easier to do? Lose 1 electron or gain 7? I'm willing to bet that losing 1 electron is easier. So therefore, lithium typically loses an electron in order to be like helium, okay? And that's what's going to bring us into the argument of ionic bonding, because when elements lose electrons, well, think about it. You have 3 protons, you have 3 electrons, you lose one electron. So now you have 3 protons and 2 electrons still in that element. In other words, you have 1 proton too many. So that's going to give lithium a +1 charge. So this lithium is going to seek somebody who has a -1 charge and go click, and they're going to connect like 2 little magnets. Not because they're sharing electrons, but because lithium gave off an electron and it now has a net positive charge and is looking for somebody who has a net negative charge. And because those 2 charges are opposite, they click together like 2 little magnets. Okay? That is a principle of ionic bonding. Whenever you have an electron be transferred to another element completely. And if you don't remember that, it is, maybe it is, there we go. Ionic bonding. Atoms lose and accept electrons from each other. In other words, the electrons are transferred completely. Ionic bonding. Is that cool? Okay. So let's recap. We have hydrogen here. How many valence electrons do we have? Well, the answer is we have 1 proton. We have 1 proton. Therefore, we have 1 electron. Therefore, we have 1 valence electron. Are you guys with me? Now we're going to go over here to helium. How many valence electrons does it have? Well, it has 2 protons because the atomic number is 2. Therefore, it has 2 electrons. Therefore, it has 2 valence electrons. Are you guys with me? This is called a noble configuration. Okay, now we're going to go to lithium. How many valence electrons does it have? Well, the atomic number is 3. Therefore, it has 3 electrons, right? However, 2 of those electrons are happy. They're in a helium configuration, in a closed energy shell. And because 2 of those electrons are happy, there's only 1 unhappy valence shell. Are you guys with me? Let's look at beryllium. How many valence electrons do we have? Well, the atomic number is 4. So we have 4 protons. Therefore, we have 4 electrons. But we can't forget that 2 of those electrons are in a happy helium configuration. So therefore, 4 electrons minus 2 electrons is 2 electrons. So this guy has 2 valence electrons. Are you guys with me? Let's keep on going. Here's boron. How many valence electrons does it have? Well, its atomic number is 5. Therefore, it has 5 protons. Therefore, it has 5 electrons. But of those 5, 2 of them are happy. So 5 minus 2 is 3. So this guy has 3 valence electrons. Are you guys following what's going on? Check this out. 1 valence electron, 2 valence electrons. 1 valence electron, 2 valence electrons, 3 valence electrons. Anybody care to guess what the next one is going to be? 4, 5, 6, 7, 8 valence electrons. Are you with me? Now here's the interesting part. Here neon, that's a closed shell on those 8 valence electrons. So when we go to the next element, all the way to the left here, to sodium, okay, the atomic number is 11. It has 11 protons and therefore 11 electrons. But of those 11 electrons, 10 are happy. So therefore, 11 minus 10 is 1. So we have 1 valence electron. What a surprise. Hydrogen has 1, lithium has 1, sodium has 1. I'm willing to bet that potassium has 1, and rubidium has 1, and cesium has 1, and francium has 1. I'm willing to bet that beryllium has 2 valence electrons, so therefore magnesium has 2, and calcium has two, and strontium has two, and barium has two, and radium has two. Is that cool? Now, we're not going to play with these. Remember, these don't deal with biology very much, except for this little guy right here, iron. Okay? So do you guys remember what boron was? Okay? That's 5 valence electrons minus 2. That's 3. So this is 3. These are 3. And these are 4. And these are 5. And these are 6. And these are 7. And these are, starting with neon, these are 8 valence electrons that are in closed low energy configuration. Is that cool? That's why these are all the noble gases. They're noble. They don't play with the common people. They're too special for us. Okay? Very neat stuff. Now, why are we talking about all this? We're talking about all this because understanding valence electrons lets us understand how chemical bonds are formed. Okay? So let's take a look at hydrogen. Here's our 1 electron. Do you see that? Here's hydrogen, 1 electron. Here's helium, 2 electrons. Is this guy happy? The answer is no, right? The answer is no, because hydrogen wants to be like this cool helium guy. He wants to be like this cool helium guy right here. Okay. Let's look at carbon. Here's carbon. 1, 2, 3, 4 valence electrons. Do you remember that? Let's go back to it. Check it out. 1, 2, 3, 4 valence electrons. Okay, so carbon has 4 valence electrons. Now, is carbon happy? No, not happy at all. It wants to have 1, 2, 3, 4 more electrons so it can have a neon configuration. And it will do whatever it can to get those extra 4 electrons. Okay. Here's sodium. How many valence electrons in sodium? Well, let's look at a periodic table. Here's sodium. It's in period 1. And we know that everything in period 1 has 1 valence electron. We know that everything in period 1, 2, 3, 4, 5, 6, 7, we know that everything in period 7 has 7 valence electrons. So these guys have 1 extra electron, and these guys are missing a single electron. Not surprisingly, ionic bonds are formed frequently between period 1 and period 7, as in sodium chloride, table salt. Okay, very neat stuff. So there's sodium. What did we say with sodium? 1 valence electron, right? There it is. All the other shells are closed. Here's the 2 electrons from the first shell to be like helium. Here's the 8 electrons of the second shell to be like neon, and has a single valence electron. Here's argon. Argon doesn't play with anybody. Why doesn't argon play with anybody? Because it is a noble gas, as all its shells are closed. See how all the shells are closed? This one has 2, and then this one has 8. Oops, my bad. And then the last one has 8. Okay. Definition. A molecule is a compound of a defined number of atoms in a defined spatial relationship. This is important. So for example, when 2 hydrogen atoms link with an oxygen atom to form one water molecule, the 2 hydrogen and the oxygen are in a very specific spatial orientation. This is important. If it's in red, you guys should know that it's important. The law of conservation of mass states that matter is neither created or destroyed in a chemical reaction. Why is this significant? This is significant because if you're carrying out a reaction in the body or anywhere in the world, what you end up with has to have the same number of atoms that you started out with. If you didn't, somebody didn't take accounting very properly. So whatever you come out with needs to equal what you started out with. Reactants must equal, the atoms in the reactants must equal the atoms in the products. As a matter of fact, this is so key that in chemistry we almost don't go anywhere unless we use what's called a balanced chemical equation. And in the balanced chemical equation, what we are asserting is that we are taking accounting of every atom and making sure that the number of products, the number of atoms in the product equal the number of atoms in the reactants. So very important. Okay, covalent bond. What do we say that a covalent bond was? We said that a covalent bond was a sharing of electrons. Okay, so let's take a look at this. I think I can do this. Hello. No, not gonna happen. Now it's gonna get upset at me. I tell you, I know what to do. I'll get rid of it and I'll bring it back and then it'll work. Is that insane? And then I'll tell it that one a little bit thicker. Okay, so how many valence electrons does hydrogen have? It has one. There it is. How about this hydrogen? Well, it has one. There it is. How many valence electrons does oxygen have? Well, let's take a look at our, let's take a look at our periodic table. Here's oxygen. So you go 1, 2, 3, 4, 5, 6. So oxygen has 6 valence electrons. Okay, let's go to it. Let's see. Click. That is so funny. This thing has a lot of hiccups. You gotta love the hiccups. Okay, so let's count them. 1, 2, 3, 4, 5, 6. Yep, sure enough, is that 6. And remember, here's a 2 that are in the closed helium shell in the bottom. So pretend that these are three amigos. They're 3 friends, and they need to buy a car, right? And nobody has enough money, so they decide to pool their resources, and they go, "Hey, if we get together, we can buy our hoopty." Nobody knows what a hoopty is. Everybody's too young. Nobody knows what a hoopty. Back in my time, a hoopty was a fixer-upper. It was a little bit dirty, it was a little bit rusty, but hey, it was somewhere to start, okay? And this hydrogen says, you know, all I need is one more electron to be happy, so I can be like helium. And this hydrogen says the same thing. He goes, yeah, all I need is one electron. So they're kind of talking to each other. And oxygen goes, well, I have 1, 2, 3, 4, 5, 6 valence electrons, and I need not 1 but 2 electrons to be happy. So they come up to a compromise and they go, you know what? Let's share what we have. So what happens is that oxygen shares 1 electron with hydrogen over here, and then it shares 1 electron with this hydrogen over here. Okay? So now this oxygen feels like it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. It's happy. And the hydrogen feels like it has 1, 2, 1, 2. It is happy too. What have we done? We have just done a sharing of electrons. This is the definition of a covalent bond. So here we are. Here's Mickey Mouse. We've got the face and the two ears. Notice that oxygen is sharing two electrons, well, is what is going on. It's sharing two electrons with hydrogen and then sharing another two electrons with the other hydrogen. So anytime that you see like an oxygen here and a hydrogen here and a hydrogen over here, and you see a covalent bond between them, let's go purple, a covalent bond between them like this, you know that that line represents the sharing of two electrons. So this line is a sharing of two electrons, and this line is a sharing of two electrons. Bam, covalent bond. Is that cool? I love how my keyboard doesn't respond to anything. Let's see, I'm going to erase now. I should have a clear all drawn. Oh, that was so cool. Okay. This is important. It says atoms of different elements differ in their power to attract electrons. The term for measuring this power is electronegativity. Okay. So I put this up in your module also, so you can open it up there as well. What I did is I went to P table, and then I clicked on electronegativity, and it shows the electronegativity of all the elements in the periodic table. The darker it is, the more electronegative the element is. What is electronegativity? It can be defined as electron hunger, the ability to pull electron density towards itself, okay? So you can see that francium down here in the lower left has very low electronegativity, and fluorine here in the upper right has the strongest electronegativity, okay? So your author is going to say that hydrogen bonding, for example, takes place when a strongly electronegative element pulls electron density away from hydrogen. And then Krogh goes on to say that those elements are nitrogen and oxygen. In chemistry, you learn that it's nitrogen, oxygen, and fluorine, but because this is a biology class and fluorine is not used in our molecules, we cut it out. And so we say that hydrogen bonding takes place between an electronegative element, which is nitrogen and oxygen, and of course, hydrogen. Why does this matter? Because the electron hunger of the nitrogen and oxygen pulls so much electron density away from the hydrogen that it reveals the nucleus. And as you remember, the nucleus has protons, which are positively charged. Why does this matter? Well, now you have a molecule that has a net negative charge on one side and a net positive charge on the other side, and it's working like a little magnet and has a tendency to make other things stick to it. Hydrogen bonding is very, very important in life. Okay. So through electronegativity, a molecule can take on polarity, a difference in the electrical charge at one end compared to the other. Okay. So these are important. A polar covalent bond exists when a shared electron are not shared equally among atoms in a molecule due to electronegativity differences. Okay. So, for example, water is polar because oxygen is more electronegative than hydrogen. So here we are. Here's a water molecule. It's got oxygen. Remember, oxygen, I keep hearing somebody tapping over there. Oxygen is one of the electronegative elements that we are aware of. So oxygen is going to pull electron density away from the hydrogens. And what this does is it provides a partial negative charge. Really? That's right. I forget that I need to make it happy every time. It makes a partial negative charge towards the oxygen, So that this is a Greek letter delta, meaning partial, a partial negative charge and a partial positive charge towards the hydrogen as the proton in the nucleus gets revealed because electrons are being pulled in this direction. So consequently, you have a dipole going right through the middle of this molecule, and is usually written like this, like a little arrow. And then we put a little plus over here to show that there's a plus sign. By contrast, take a look at this. This is methane. So let's look at carbon and hydrogen, okay? So we'll go back to our, oh, okay, there we go. We'll go back to this. Here's carbon, here's hydrogen. The electronegativity is right underneath it. So the electronegativity of carbon is 2.55. I don't know if you can see that. We can make it bigger. 2.55. And the electronegativity of hydrogen is 2.2, making carbon slightly more electronegative than hydrogen. So what that means is it's not gonna work. There we go. What it means is that carbon is going to pull a little bit of electron density in that direction, and in that direction, and in that direction, and in that direction. Okay? So imagine you have four guys playing tug of war with one big guy so strong that they can pull the same amount from the four. What's going to happen? The short answer is nothing. Absolutely nothing. This dipole cancels this dipole, and this dipole cancels this dipole, and so you end up with a non-polar methane molecule. So in other words, whether a covalent bond is polar or non-polar not only depends on the electronegativity of the atoms, but on their three-dimensional orientation in space. In this instance, the three-dimensional orientation in space made all four dipoles cancel each other, and consequently we end up with a non-polar covalent bond versus a polar covalent bond. Is that cool? I love this. Okay. Ionic bonding. So two atoms will undergo a process of ionization when the electronegativity differences between them are great enough that one atom loses one or more electrons to the other. Electrons are completely transferred in ionic bonding from one atom to another. This process creates ions, atoms whose number of electrons differ from the number of protons. Let's see. So, as a consequence of this ionization, which causes electrons to either be given away or received, you end up with oppositely charged particles that attract themselves and form ionic crystals. Okay. An example, of course, is table salt. And here, sodium gives up an electron to chlorine. Let's see if you guys remember why that is. Okay. Let's go back to our periodic table. So here's our periodic table. Here's sodium. Remember that sodium is a +1. So +1 means what? It has one extra electron there, right? In other words, there's one valence electron that is unhappy. And look at chlorine. Chlorine is over here. So sodium has one electron. How many electrons does chlorine have? Starting here, we go 1, 2, 3, 4, 5, 6, 7. So it needs one electron to become like argon. So what happens? Sodium gives its electron to chlorine. When it does that, sodium ends up with a charge of +1 because it's got one less electron than it has protons, and chlorine ends up with a charge of -1 because it has one more electron than it has protons, and these two end up attracting each other because a +1 and a -1 is like having the south pole and the north pole of a magnet. They just go click, and you end up with what's called an ionic crystal. Here it is, okay? So there's a valence electron of sodium, and here's a 1, 2, 3, 4, 5, 6, 7 valence electrons of chlorine. This electron is given away. This guy now has a +1, and this guy has a -1. Now, something that you need to realize about this is that when this electron gets transferred, both sodium and chlorine are considered ions. So ions is a charge that is instilled on an element as a consequence of it gaining or losing electrons. So sodium ends up being an ion, a +1, and chlorine ends up being an ion, a -1. Okay. All right. That's where we're going to stop right now. We'll continue the next section in just a little bit.